Hi, and welcome to Test Prep for ENGPHYS for test number 4 in 2018. What we're going to be doing is looking at trusses and frames, first looking at just truss problems. Now, we actually have to look somewhere different than the past tests in the previous few years, because those tests always covered a little bit more content at this point. So we would take a week off and have a big sample midterm typically in the past, which means we wouldn't get a dedicated test on just trusses and frames. So there was always distributed loads and internal forces and bending moments in the content for those tests. So for now, we need to be a little bit more creative to address the content that we do have in the test. So first up is a question from the 2015 first sample test, and this is a partial truss solving question. So it asks us to find the force in members ED, DF, EF, and EG. Now the standard way to do this, if you don't need the whole truss, you just need these sorts of things, is to use the method of section. So we're going to do that, and we're also going to analyze this with the method of joints a little bit to show what that would be like. Okay, so method of sections, the plan is that first we are going to solve the system for enough of the reaction forces that when we section the system, we can look at just one side and then see how things are going to be behaving. Okay, so let's have a look at that. The plan to do that sectioning, to look at EG, EF, and DF, would be to we can look at just the right side once we figured out what the reaction force at F is upwards, and then we don't need to figure out what the reactions at B are in the horizontal and the vertical. Now ED is a zero force member, because if it is applying any sort of force, then it would be completely unbalanced at D. So at joint D, we've got a force to the left from BD and a force to the right from DF, assuming they're all in tension, and we've got a force up from ED, but nothing else to balance that. There's no other thing that can exert a force in the downward direction or the upward direction there. So that means we can't have any force in ED, so that's a zero force member. Same thing could be said for CB and GF in this system. Okay. So let's do our equilibrium of the entire body in order to figure out what the force at F is. And let's see, we can get an equation here, and we'll write out that the net torque about, say, point B is equal to 0. And let's take the torques in the counterclockwise direction as positive. So what would we have? We'd have 2 times 0.4 meters, so that's 0.8 meters times the reaction force at F in the y direction. And we are also going to have so rotating this way about B would be from this force. So that would be 8 kilonewtons times 0.4. 0.4 meters times 8 kilonewton. And then we're going to have a force going in a torque going in the opposite direction times 3 times 0.4. So minus 1.2 meters times 14 kilonewtons. And that's an equation we can use to solve for Fy, so the reaction force in the y direction at this support. Now once we've got that, we figured out ED is 0, we can section this system between those members that we're interested in, EG, EF, and DF. Let's grab some paint here. And the idea is that this whole half of the thing has to be in equilibrium too, right? Maybe another way to do this is like that. And we'll just get a whole new window. And yeah, now it's on a white background, so we can draw on that a little bit more easily. So what do we need? We've got that this thing by itself is in equilibrium, so we've got the reaction force at F already figured out. Let's do something like that. Okay, and we've got some reaction We got some force there. We got some force there, and we've got some force going out that way. Okay, so these will be with reference to the original labeling. This force would be EG. Down here in the middle, we got EF, and over here, we've got DF. And then this one up at the bottom was FY, up from the bottom there. Okay, so there's our redrawn free body diagram. I can say section between EG and DF would give us this. Okay, so we figured out what Fy is from this first equation, the equilibrium of the whole body. We could have used that by writing the net force in the x direction and net force in the y direction to figure out the other reactions at B. But we don't actually need them to then just look at the equilibrium of the whole right-hand side using method of sections to solve for those other forces. So we have three unknowns here since we've already found what Fy is from this first equation, and we'll be able to get three equations from the net force in x being 0, net force in y being 0, and net torque about any point being 0. Okay, so let's take, so here I've included a little bit more of this member, but imagine that these forces are really just coming from this, this pin there, if you like. So what do we got? We got the net force in the x direction is equal to 0, which is equal to negative EG minus DF minus EF. And now what would be the x component of this? That would be, it's a 4 along the horizontal and the 3 vertical. So the hypotenuse must be 5, root of 3 squared plus 4 squared. So we've got the horizontal component would be 4 over 5. And the vertical component would be 3 over 5. Right. So anyway, minus EF times 4 over 5. And then there's nothing else in the horizontal. So that's one equation. We have the net force in the y direction is equal to 0, which would be, I guess I need more more symbols here because I already called that thing up there Fy. That could probably get confusing. Net force in y, maybe? Sure. Okay, so that would be Fy, and it would be EF times the EF's vertical component, which would be 3/5 times EF, and anything else. We've got minus 14 kilonewtons vertically. Then we have a torque equation. We can do this about any point that we like. So let's say the sum of the torques, again, about point F is equal to 0. And what are we going to have there? We've got these two forces, DF and EF, are collinear with point F, so they create no torque. Fy creates no torque about that. That's collinear too. That's why this is such a great spot to pick. So we've got EG times 300 millimeters up. So let's do 3 times EG. And we've got 14 kilonewtons in the opposite direction. So minus, and that is how far away? 400 millimeters. So 4 times 14 kilonewtons. Now you notice I just put 3 and 4. So the reason is, since we have this equals to 0 anyway, we can divide the whole thing and multiply it by a constant without changing it. So here we've gone and divided away the we've gone and divided by 100 millimeters across this equation, and that still leaves us with something that's true. So this lets us solve right away for what EG is. EG is going to be 4/3 of 14 kilonewtons. Then we can take the Fy that we solved from the first part and substitute that into there, and sub to get EF, and then we get both of those things subbed into here to figure out what DF is. Okay. Okay, once we've got that all laid out, actually solving it is not too bad at all. So we're going to say restart, solve 0.8 times Fy plus 0.4 times 8E3 minus 1.2 times 14E3. Next equation, negative EG minus DF minus EF times 0.8, which is 4/5. And then Fy plus EF times 3/5. I guess we could have said 0.6 minus 14E3. And 3 times EG minus 4 times 14E3. Okay, and there we go. So we've got Fy is 17K that ended up being positive. EF is negative 5K. So EF was in compression. EG is fairly large, it's like 19K, and it's pulling over to that side. And DF is in compression as well. That's pushing back in the other way by about 15K. So that's the solution we got using probably the fastest way to do this, which is method of sections. If you wanted to know what all of the forces were in this, then you'd be better off not bothering with sectioning it out and doing that sort of fancier way, but just kind of brute forcing your way through the whole thing using the method of joints. So let's give this a shot. We're going to imagine that we've got a force applied in the vertical direction at B, and this is going to be By. We've got Bx there over to the right, and we've got Fy again pointing up as our reactions. Bx, By, and Fy. Okay, now we'll collect that. There's our free body diagram for the whole thing. So we've got, with method of joints, you kind of go through joint by joint and then add up all the forces on it. And this one, again, even though it's method of joints and we're going to be brute forcing it, is not quite so bad because we've got some zero force members, so we can just ignore the CE and AC, you know, that those are the same, or we can write it out as a whole equation. So let's just call that ACE or AE or something. The force in this one has to be, in AC has to be the same as CE because there's a zero force member there, so it's only those two connected. And same thing with BD and DF and EG and GH. All right, so then how many unique pins do we have to look at, since we don't really have to look at that one, or that one? Well, we've got 1, 2, 3, 4, 5. So when we're done writing this out, it should be 5 pins, each giving us 2 equations, would be 10 equations, 10 unknowns. So let's give it a shot. Maybe we'll try write in Maple to save us the time of having to rewrite it. Okay, so let's just go in alphabetical order there. At pin A, we've got a force in the x direction. What do we have? We have AE to the right, and we've got plus AB, the horizontal component, times 0.8. So that's the 4 horizontal over the 5 hypotenuse, and that's it for the x component. When we don't say equals 0, then that's implied for the solve command, which, by the way, I guess we should write. Okay, solve that thing, and that means that equals 0. The vertical, we'd have negative 8E3, and we've got, and that's negative because it's pointing down on the thing, and then assuming the whole thing's in tension, we've got a pulling down force from AB as well, so minus AB times 0.6. Next, at pin B, we've got BX, we've got BF, we've got minus AB times 0.8, the horizontal, and we've got plus BE times 0.8, horizontal component of that one. Then in the vertical, we've got AB times 0.6 plus BE times 0.6 plus BY, remembering that BC is 0, so forget that one. Okay, AB we don't have to do, C, D we don't have to do, E in the horizontal, we've got, what do we call that, AE. The hardest part is sort of remembering what you called the thing. So let's see, we've got negative AE, and we've got minus BE times 0.8. That's the horizontal part of member BE. And we've got plus EH, the most Canadian of variable names, and we've got plus EF times 0.8. 8 again. Okay. And that should be it for the horizontal for joint E. Then the vertical at joint E, we don't have to use this one, remember, because that's just that's a zero force member over here. So we've got negative BE times 0.6 minus EF times 0.6. So by symmetry, you can, I guess you could use after this is a zero force member, you can use symmetry to say that this force has to be negative this one, which clears up a lot of, well, that's kind of what we expect at the end based on that aspect. Okay. I guess we can't really go further with that because of the extra members in there, like with what Fy is doing and all that. Okay, so that's E. F is next. Minus BF, horizontal, minus EF times 0.8 plus FH times 0.8. And then the vertical component, we'd have EF times 0.6 plus FH times 0.6 plus Fy. And then finally, since we don't need G, we're at H. H horizontally would be negative EH, because again, everything's in tension, so that's pulling from there, minus FH times 0.8. And the vertical would be minus FH times 0.6 and minus 14E3. So as a check, we should have every odd line having only 0.8s in them because of the angles involved, and every even line having only 0.6s where there's a multiplied by something because of the numbers involved. So that should be it. Let's see how we did. Okay, we don't see any, we see that we solved for everything, and did we get the same answers as before? BF, which was DF before. Looks like it's the same number. That's a good sign. ACE we didn't solve for. What did we solve for? We solved for previously EG, which is now EH. Okay, that's good. And we've got EF, also solved for. FY is the same thing. Okay, so it looks like we were consistent, didn't make any mistakes, or if we did, then we made the exact same mistake twice. So hopefully that's not what happened, because that would be a little bit harder to figure out. So method of joints, a lot more brute force in writing the thing out, but did solve for all the different parts simultaneously. So in the interest of doing kind of a tricky frame and truss question and dealing with some of the things that you're going to need to do more advanced problems with this, I'm going to do one of the past test questions and just modify it so that it doesn't have the stuff we haven't dealt with in the course yet. Okay, so truss and frames solving. This is the 2016 test 4. Remember ABE, that's this one there, supports a mass with weight 1 kilonewton at point E and is connected to a large block to its left via a fixed support at point O, 10 centimeters to the left of point A. All members are made of a light acrylic and have a negligible mass, except for ABE, which is made of steel and has a total weight of that distributed uniformly along its length, but we're not going to deal with that. So all members are made of a light acrylic and have a negligible mass. End of story. Great. Yeah, coordinates of the points in meters are, there's the origin, which is 10 centimeters left of A, and then we've got B, and C is up there at 0.5, 0.8, D is 0.05, 0.8, E is 1.3, and 0. Okay, remember ABE extends from point O to point E. The block on the left, which ABE is attached to, is fixed. Show that the system for the equilibrium of the 3 truss elements and the frame leads to 5 equations and 6 unknowns, and determine what those equations are. So we don't actually have to solve it yet. We're just going to show that this whole system leads to 5 equations in 6 unknowns, meaning it's indeterminate. Okay, so this is still going to be true, ignoring the distributed load from the weight of ABE when it was made of steel. And so we're going to be able to demonstrate the key parts that this question was getting at anyway. So that's good. That's some good stuff. Great. All right. I guess we need a new, 800 by 600, and nothing really special about that size. Just picking that. Okay. So here is the setup, and then we're going to we're going to draw some separate free body diagrams for the different parts of this. So we will need a free body diagram for this frame, and that we can get by sort of cutting some of the picture and then drawing the force vectors on it ourselves. So we've got a vector up this way. We've got a vector up that way. On the truss elements, it's going to be collinear with the direction from one pin to the other one, which happens to be just along the truss. Since these truss elements are straight, we've got a weight force going down. And then at A, we've got a force horizontally, not at A, at O. We've got a force to the right, we've got a force up, and then we are going to have a moment as well. So here's a trick to drawing a moment. I'm going to pick a different color so I can label it. Maybe seem to like green for these moments. And then you can draw something like that. And then in paint.net, grab the different points of this line and bend it into some kind of a curve. Ideally, we want a circular curve, but this is going to get the point across. So the moment going that way. All right, so now hitting T to switch the keys. Let's call this MO. We're gonna go back to the violet color here, and we've got OY, OI, and OX, and then we've got what would this be? AC. This one is BC, and this one is what do we call that? Maybe like MG, since we know the mass of that thing. Sure. All right, cool. So there's our free body diagram for the frame. Draw a FBD for the frame. And there we go. Okay. So we can, we're going to have a system of 3 equations and 3 unknowns. Sorry, not 3 unknowns, 3 equations for the frame. And what don't we know? We've got 500 newtons, so we know mg. We don't know any of these 3 reactions, and we don't know those 2 truss elements. Then the other thing we could draw a free body diagram for is point C, which is going to give us 2 more equations and 1 more unknown. So why don't we go ahead and explicitly show what we're talking about with that when we draw the FBD for point C, just sort of leaving the truss pieces in there to show the angles that we're talking about. We've got pulling that way. Whoops, oh, not that. Let's just draw that along the truss. We've got another one which is going down like that, and we've got a horizontal one, holding shift to make it snap to horizontal. Okay, so what do we got? We got DC, we've got AC, and we've got BC over there. Okay, and I guess we could hit S to shortcut to the select. So there's our free body diagram, bonus FBD for joint C. Okay, and that means we're going to get 2 equations from here, 3 equations from here. We don't have a torque equation for this one. Because pin D is only connected to a truss, it can't provide a Y and an X component. Really, it can't provide a Y component, because then the truss member won't be able to balance that, right? If it did have a Y component, then it would have to be balanced by a Y component on DC from this side, which means we would have a torque and the thing would spin, but it can't resist rotating because it's pin supported on this end. It can't resist a pure torque. So that means we can't be applying a couple to it, which is a pair of forces that are equal and opposite but not collinear. So we need the reaction at D in the Y direction to be 0. So there's none of that. So okay, what do we have? We got DC, we've got AC, we've got BC, we've got the 3 reactions at this fixed support. So that's 1, 2, 3, 4, 5, 6 unknowns, and the equations we got are 1, 2, 3 for force in the X, force in the Y, torque about some point, and force in the X, force in the Y for joint C are 0. So 5 equations in 6 unknowns. So we could write them out. We've got sum of the forces at C are equal to 0, which gives us the x component, negative dc, minus AC. And now, you know what? Let's put the whole thing in vector notation. So this is another way that you can do it. When we've got crazy coordinates for the different things, and it's not just a pure horizontal and easy angles that we can write out, then it makes a little bit more sense to write it in a bit of a more arbitrary notation. So DC only going to the left, which we could say negative DC 0, and then we've got plus AC times R hat from C to A, plus BC times R hat from C to B is equal to 0. Now we'll say where R hat CA is equal to negative the unit vector from A to C, which would be the coordinates of point C minus the coordinates of point A, so as position vectors over its own magnitude, RC minus RA. All right, so there's that unit vector. And now we've got a vector equation for the net force at C. We can also do the same thing for the net force on OABE is equal to 0. And what would that be? We've got OX and OY, which I guess we could say is vector O, not to be confused with 0 because it's a little bit wider. I don't know if I like that. Maybe OX and OY. Then we've got AC times R hat AC plus BC times R hat from B to C, and then negative mg in the vertical direction. Okay, so there's the vector equation for the force on OABE, and we just need the torque on OABE. So we can pick any point we like. How about the torque about point O? Why not? The sum of the torque about point O is equal to 0. All right, and this would be equal to, we've got sum of the torque in which direction? Let's say that sum of the torque in the, let's say out of the page is positive. So using the right-hand rule, that would mean MO. MO is positive, and we've got also a positive torque created by AC and BC, but a negative torque created by mg at its distance. So AC, we need the vertical component of that and its distance away, which would be 0.1 times AC's y component, which would be, how can we refer to AC's y component? Maybe if we take R hat AC and we dot that with J hat. Okay, I guess that's a way to write that. Yeah, so we'll dot that with the, we'll just extract the y component that way. That's a way to write the y component of AC. Sure. And then we're going to add to that the distance to B, which is the, which is 1 times R hat BC times J hat. Oh, and this also needs to be multiplied. So that's sort of the force, the distance and the component of the force, but we need the force itself. So that's AC and BC. And then we've got minus the mg at its total distance, which is 1.3 mg. Now, a couple things. So we didn't have to multiply this by any sort of vector thing to get its component because it's already perpendicular. All of mg is going perpendicular to the line to that force, so it's like a sine of 90 degrees. These ones, by extracting the vertical component, we've got it's the same as taking the sine of the angle they make with the moment arm. The forces right at the origin don't create any torque about the origin. We should be able to write this torque equation about any point and get the same kind of expression. That's not going to be, it's not any different if you write it about some other point. And the last thing is I didn't have to write the length units here because in a static equilibrium problem we're adding it all up to 0 anyway, so we could just divide, so it's still equal to 0 even if you don't write the units in every term. Okay. So, as promised, we've got 1, 2, 3, 4, 5 equations in 6 unknowns: DC, AC, BC, OX, OY, MO. Okay, so next, moving on. Suppose the truss system is installed as an afterthought, just in case, and the system changes so that the force in the trusses is guaranteed to be 0. So that means AC, BC, and DC is 0. Determine, and we've just got this this frame. Determine what the peak shear stress and bending moment are and where each occurs. Okay, we can't do that yet. That's going to be some stuff for next time. So let's instead determine the reactions at O. Yeah. Totally cool. This is something you would have had to do to answer what the original question was anyway, so it's still a big part of that problem. So in order to determine the reactions at O, we essentially just take the equations that we've got for the net force on OABE, but without the truss parts, and then set that, and then solve those. So what do we have for that? We've got mg, we can ignore that stuff, and MO. That tells us what MO must be right away. MO is 1.3. Oh, you know, hold on a sec. I messed this up. So we have to, because MO doesn't have a length in it, we weren't able to divide that. So we do need to write this in as meters. Okay, great. So that means MO is going to be 1.3 meters times mg. So multiplying the 500 newtons by 1.3, what's that, 650 Newton meters should be what MO is. You could have solved that with Maple, no worries. And then you can do the same thing for the force balance in X and Y. And it's actually really quick. So the force in X, there's no other forces in X anymore. So we've got just 0. And the force in Y is going to be mg. That's the reaction force in Y. So there we go. We've got our reaction forces. Problem solved. No sweat. Okay, last part. Suppose the truss is installed so that the reaction moment at point O is 0. So rather than setting the force in the trusses as 0, so the moment is supplied, we've installed the truss so there's no reaction moment. And the system's installed to keep it that way. Solve for the reaction forces at point O and the force in each truss member. State whether each truss is in tension or compression, and draw a shear force and bending moment diagram for ABE. We're not going to do that. That's next week. Determine what the peak shear stress and bending moment are now and where each occurs. We're not going to do that either. Compare the support system in part 1 to part 2. Which support system for which is member ABE more likely to break from shear and from bending? So we're not going to do that either. Lots of fun stuff to come soon, but for now, all we're going to do is solve for what the truss forces are and the reaction forces at point O, assuming the reaction moment at point O is 0. Okay, so going back up to this equation set, we've got MO is now 0 by definition, so we've just sort of said that the thing's 0, and we're going to try and solve the equations that we get. Okay. So in order to do this, I'm going to give you some tricks for solving, writing out these unit vectors. First, let's just see how we could do that by default. So we've got these coordinates, and you could say, you could write out what the forces are on things by converting them into x and y components using the directions that we've got associated with this based on point A and point C. So let's do the brute force way. First we'll say mg is equal to 500, and we've got the force on BE would be OX plus AC, and we need its x component. So its x component would be how far over A is to C, which would be 0.5 minus 0.1. That's the x part of it, so 0.4. And then we're going to divide by the square root of its rise, 0.8 squared, plus that 0.4 squared. Okay, so that'll be AC's x component. And then we're going to subtract off BC's x component. I guess I'll write this with a capital to keep the notation. BC and its x component, we're going to look at B to C. So that's a negative 0.5, but we've already subtracted. So we'll say 0.5 over the square root of that 0.5 squared plus 0.8 squared. So what I'm doing is I'm looking at the difference between point B and point C, how much rise we have, which is 0.8, and that's the y component of that, squared, kind of breaking it up into its x and y components by taking the x part and then dividing by the hypotenuse. So that's how you get the x component. Okay, now the y component will actually be a pretty similar equation, but here instead of that we've got 0.8, and for the BC we've got a plus, again 0.8 over its part, and then we're going to subtract mg. So that wasn't so bad. What next? We've got the torque about some point. So the equation for the torque about some point. If we take the about 0.0 part there, then we've got 0.1 times the, we needed the y component of RAC, which we've said is this fraction of AC. And then we're going to add to that a 1 times the y component of BC, which we've got right there. And we're going to subtract 1.3 times mg. So there's the torque equation. Next up, we are going to need what's going on at joint C. So in the x direction, we've got negative DC, and then we've got minus AC times its x component, which I believe was 0.4 over this same thing. There we go. And then we've got a plus the same BC. So as a check, you expect that the other side of where this truss is acting is creating the opposite kind of a force as it was in the first part, and that seems to be true for each of the truss elements. And then so that's in the x, and then in the y direction we've got the again the opposite of what's going on with AC and BC there. So we've got minus for the AC and a minus for that BC component. Okay, so that should be it. Yeah, we were able to solve for everything. So we've got OY has to be 500, AC is negative 807, 812, 812, and 851. Now, as a bit of a check, we can go back to the original problem and try and solve it different ways. So maybe we can think about sectioning parts of this. We don't want to section through the frame since we don't know what the internal forces of that thing would be, although that method is going to be very useful when we get into internal forces in things besides trusses. So we do have to be careful about what we're saying is an equilibrium, but then we can do we could possibly do some checks with that. So let's see, we've got the whole thing is in equilibrium, so about 0.0. ignoring the moment in this new configuration, we'd expect that the distance over to E, 1.3 times mg, should be equal to the distance up to D times dc. And what that says is that dc should be equal to what we get by solving dc times, what was the distance up to D? It was 0.8. And that's supposed to be equal to the distance over 1.3 times 500. So let's solve that. DC is 812.5. Now, because we did such a different way to solve this first set of equations, where we didn't really look at the external, but we got the same result for that, that's a great way to check if you've made some kind of a mistake. Let's talk about more pitfalls. One easy thing to do is, while you're writing this out in a later equation, you say, oh, this is for CA, right? You forget to call it AC. So what do you think is going to happen if we do that? Well, now we've got a new variable in there, and so Maple's going to think, oh, that's just a different thing. We have more variables than we have unknowns, and it'll spit something like this out at you, where it says, okay, DC can be whatever, and then it's going to give you the rest of the equations in terms of DC if necessary. Yeah? So that's a hint that probably there's a variable double named in there. Okay. Oh yeah, there we go. Right. So there's that's something to watch out for. Now I know what you're thinking. You're thinking, all right, that's all well and good, but I really like vectors. Is there some way that we can just type in these vector equations and use that to solve for the setups for the forces, even in an even more vectory way than we're doing it here? And the answer is, fortunately, a resounding yes. So let's start by restarting this. And now what we're going to be doing is starting by typing in the position vectors for all of the different points. So RO is, let's check out this new package. This is beyond the Maple that we had before. With linear algebra. This is including a package in Maple, so adding in the linear algebra package, RO is going to be the vector object of 0, 0, like that. You put it in just brackets, and then square brackets, and then round brackets, and there we go. We've got a vector. Cool. Let's add in more. RA is vector 0.10, and there's that. We'll suppress that output. RB is going to be 1, 0. RC is 0.5 and 0.8. RD is 0.05 and 0.8. And RE is 1.3 and 0. Okay. Right. Now, what's the point of that? Well, now we can define some unit vectors. So check this out. First of all, we need to know a new thing. So we can do norm of RE or RC, let's say, 2. What this does is compute the root of the sum of the squares. Technically, this is the 2 norm of the object, which is sort of the square root of the sum of the squares of the things. You can also compute different norms. So let's see what the 1 norm gives us. That's for RC 1.3, which is actually just the first root of the sum of the first power of the objects, of the elements. So you see that would indeed give you 1.3. You can use higher norms. So let's say 3. This should be the cube root. So of the sum of the cubes of these things. Right, but we're actually just interested in the square norm pretty much all the time in physics. So we're just going to do norm 2 for this stuff. Norm RC 2 to get the root of the sum of the squares of those components. Yeah. Okay. So next, what we can do is define unit vectors like so for the things we need unit vectors for. To get the unit vector from A to C, what we can do is say RAC is equal to, well, first let's go RC minus RA, and then RAC is mod over norm mod 2. Think for a moment about what this is doing. First we compute position C minus position A, and then we take that thing and divide it by its own norm to get a unit vector in the same direction. So there we go. The norm of this thing should be 1. Ta-da. Now we've got a syntax for writing out unit vectors quickly and effectively and efficiently in Maple. Now we actually didn't need most of these coordinates defined in order to do that. So to get the unit vector from B to C, what we would do is RC minus RB. RBC is equal to mod over norm of mod 2. And what's nice about this thing is that if you're defining a bunch of unit vectors, you can just copy paste this onto the next line. From D to C, and then paste it in. Okay, so there you've got all the different unit vectors that you need for a problem. That's defining unit vectors. Now, how are we going to use that in order to write out the components a little bit more easily? Well, now that we got that, we can write out the force here. Let's start with the torque equation. So the torque equation for this this part would be the y component of AC is what we needed when we were writing those things out. And you can get the y component by just subscripting it. So RAC is that, and if you want the y component, RAC second component, you can extract like that. So 0.89. Okay, let's check that out. So we've got 0.1 times RAC second component times AC plus 1 times RBC's second component times BC minus 1.3 times mg. Okay, and now in the previous version of the problem, we could have written out that equation using this syntax instead. So there's a way that you could write out the torque equation using vectors a little bit more concisely. You can also do vector versions of the other equations. So you could say the C equation would be equal to vector negative dc and 0 plus AC times R, well, we need RCA, so that'd be negative RAC plus BC times negative RBC. And there we go. We got a vector version of the equilibrium at 4C. Equation ABE would be equal to, similarly, vector OX OY plus AC times RAC plus BC times RBC plus another vector 0 and negative mg. So there's the two vector equations we've got. Maybe we'll call this one the torque equation. Then we've got so we've got the equations that we need to solve. We need to define what mg is, and it's the 5 equations in 5 unknowns: OX, OY, AC, BC, and DC. Now to solve this, we need to kind of split up those different equations. So we need equation tau we need equation C first component, equation C second component, and the same thing for equation ABE. And we should get the same stuff as before. It looks like a lot of familiar numbers. 812, 812, and then AC is negative 807. Yep. So same thing as before. With the vector form of it, it's not any faster. In fact, you could look at the time index. It's probably a fair bit slower to do it this way. But boy, is it ever vectory. Isn't that beautiful? Isn't that something? So next thing we could do, if you like, and you're writing out a bunch of these different vector equations, suppose you say, I know what you're thinking now. You're saying, okay, now that's all well and good. This is fantastic, but I mean, this part at the end really kind of gets annoying, right? Isn't there a better way that we could sublist this thing rather than calling it equation C, equation ABE? Couldn't we call it like equation 1 and then equation 2? And then refer to those things a bit more easily. So let's go equation 1, 1, equation 1, element 2, equation 2, element 1, and equation 2, element 2. Does that work? It does not. Or at least it doesn't list it very accurately. So now if we say equation, we don't it doesn't know how many elements are in that list, but we can still sort of sublist it like that. So it did work for this thing, but equation is not really a full list of things there. So suppose you don't want to write out this thing at the end. What you can do is you can use a sequence variable. So let's try that. Sequence. First of all, what does sequence do? Sequence I squared, I equals 1 to 5. Whoops, is it just seq? Yeah, so SEQ short for sequence. What this does is it says whatever you put in here for this loop variable, and then it just puts them in a list. So what you can do is you can say, what do we need? We need sequence of equation I 1 and I equals 1 to 5, and we're also going to need equation the second component. So what could we do with that? How about this? Sequence of sequence equation I, j, I is 1 to 5, j is, well, not 1 to 5, 1 to 2, j is 1 to 2. Ta-da! What did that do, by the way? It just reproduced the equations from inside those vector forms. So yeah, by looping and getting into some not so bad programming syntax in Maple, you can really try and get a whole bunch of optimization out of writing this expression down, which can be helpful if you're solving a whole bunch of equations at once. Okay, hope you've enjoyed. Have fun.